Okay, so we are back live in YouTube, and now I'm going just to start the recording. Okay, so we are recording now. So Amilcar, if you want to introduce the next professor here, thank you.
Okay, welcome all back to this second session of our symposium. It's an honor to present Dr. Phillip, the next speaker. He earned his PhD in astrophysics at the University of Oxford. Then he had done some couple of postdoc at Berkeley, at GPL Caltech, and also at University of Oslo. He is currently a lecturer in cosmology at Queen's Mary University of London. He is also member of SKA, HERA, and Vera Rubin Observatory. He's going to talk to us about 21 centimeters intensity mapping, which is quite appropriate for our community. So, welcome, Dr. Phillip. It's up to you. You can start anytime you want.
Oh, thank you very much. It's a real pleasure to be with you. I hope you can all hear me and see the slides okay. I'm sorry I couldn't be there in person for obvious reasons, like many others. But I still hope we'll be able to have a fun and interesting session about 21 centimeter intensity mapping, which, of course, I'll say this, it's one of the most exciting fields in cosmology at the moment. And there are lots of fun problems and really exciting scientific opportunities to do with it. So I want to give you a kind of overview of some of the basics of 21 centimeter intensity mapping. I know some of you will already be all too familiar with these basics, but I think it's good for everyone to get a bit of an overview. Now I'll talk about some current experiments that are going on in this area. Some of the more recent findings. I'm going to focus on a particular experiment I'm involved in called Meerkat, which is a precursor to the square kilometer array. I know you're going to hear about Bingo in an hour or so, I think. And then I'm going to talk just about a few of the different interesting scientific applications that intensity mapping will be really good for if we can iron out all of the bugs and really make it work well, which at the moment it's still a very young field, so there are lots of bugs to be fixed in the meantime. So as we go along, please do let me know if there are any issues with sound quality or if things are going too fast or too slow, and I'll do my best to respond. Okay, so let's get started. So here's an outline of what I'm going to talk about. I'll do the basics first. I think that's a good place to start. And talk a little bit about the experimental landscape. This is mostly an excuse for me to show you some pictures of cool pieces of radio equipment. And then I'll talk about a little bit about some of the characteristics of real 21 centimeter intensity mapping data. It's one thing to kind of look at this stuff from a theoretical perspective. If you do that, it all sounds really great. But when you start really working with the data, there are lots of fun problems that you very rapidly come across. So I'll try and share a bit of experience to do with those. Then I'll talk about Meerkat for a little while because it's reasonably similar in some ways to the Bingo experiment that I know some of you are very heavily involved in. And then I'll talk a little bit about things, scientific applications beyond the baryon acoustic oscillations. So hopefully most of you already have a bit of background knowledge about astrophysics or cosmology. If there are people who need me to go a bit slower, I'm not sure the best way of going about it, but if you're able to raise your hand or leave a comment or something like that, hopefully one of the hosts can give me a nudge, and I'll be happy to explain some of the details if you're not familiar with them. Okay. So yeah, is that okay?
Yes, it's okay. Just to.
Yeah, fantastic. Okay, so to start with, this is really all about the large-scale structure of the universe. So what we're really interested in doing is making a map of as much of the observable universe as we possibly can. And the reason for that is that all this structure in the universe it comes from somewhere. It comes from things that happened very early on in the universe's history. We have this theory of inflation that we suppose explains what happens in the first instance after what we call the Big Bang. The structures that were put in place back then, very early on in the universe's history, then evolved using straightforward, or we think of them as straightforward physical principles, mostly to do with gravitational collapse. So the way the structure looks is telling us something about our theory of gravity as well. We normally assume general relativity, but if we have some other theory of gravity, that should leave an imprint in this structure. And also, it should tell us a lot about what's actually going on a scale of galaxies and clusters of galaxies. There's lots of interesting astrophysics that goes into producing the individual objects that make up the large-scale structure. So measuring the large-scale structure of the universe is a tremendous preoccupation of cosmologists. We know that it contains this wealth of information about everything from fundamental physics to the way galaxies and maybe even our own solar system formed. So we know we want to gather as much information about the large-scale structure as we possibly can. And the way we do that is by trying to make maps of it, and then by analyzing the statistical properties of those maps. So the structure we see in front of us, I've shown you an example from a simulation here by Kim et al. from 2009. What you can see is that this is a simulated map of the large-scale structure of the universe. And along this kind of wedge shape, you're kind of looking further away, so at further distances, or further back in time. And so this is kind of how we see the universe anyway, because the speed of light is finite. And so you see that the fluctuations were smaller at early times, very far away from us now, and the structures grew. What we're trying to do is analyze the statistical properties of those structures to try and figure out all these the properties of all these physical processes that must have caused the structure to form. There's a problem, of course. There always has to be a problem, otherwise we wouldn't be talking about it. And that problem is that most of this structure is formed from invisible dark matter. So we think that somewhere roughly in the region of about 80% of the matter in the universe is dark matter. We probably think that's some kind of new particle that we've never observed before, that interacts very weakly with other types of matter. But the main point is we can't see it directly, and so we need something that traces the dark matter. Remember, where most of the stuff in the universe is, where most of the large-scale structure is. We need something that tells us where the dark matter is, but that we can see. And so this is really the context for 21 centimeter intensity mapping. We have this interesting and very versatile tracer, which is neutral hydrogen, and we're using that to trace where all of the dark matter and therefore where all of the large-scale structure of the universe is. So what is intensity mapping? Here's how it works. In the top of this figure, you can see I've just kind of simulated a distribution of galaxies. Okay, each point is supposed to be a galaxy. A galaxy would be a good tracer of the underlying dark matter distribution, the underlying large-scale structure. So where we see more galaxies, we know there's more matter there. Where we see fewer galaxies, so for example, in this picture, you can see a void region where there are no galaxies. We know there should be less dark matter as well. So we can use galaxies as a tracer. The problem is galaxies, there are many of them out there. They're quite bright, but even so, it's very time consuming and actually quite expensive to detect them. You need a dedicated telescope that can make spectroscopic measurements to find out exactly where that galaxy is in space. That takes a long time. Instead, intensity mapping tries to go straight for the information that we care most about, which is the overall distribution of all of the galaxies on very large distance scales. So most cosmologists, not all, but most cosmologists don't particularly care where an individual galaxy is. We care about what the large scale pattern is, what the large scale distribution of the galaxies is, where the voids are, the filaments, the clusters of galaxies. Where an individual galaxy is, we don't really want or need to spend time determining that. If we could, we just ask for a snapshot of the large scale structure. And that's what intensity mapping gives us. So intensity mapping is where we say, instead of looking for individual galaxies and trying to measure their positions and redshifts, what if we kind of take some kind of telescope where we can kind of blur our eyes and just see, the very largest scales? What if we only pay attention to the emission coming from many galaxies as a whole over these large distance scales? That's what intensity mapping gives us. It can't, in the way we normally deploy it, it can't resolve individual galaxies. Instead, it collects light from many, many galaxies. You can imagine each pixel of your image containing many galaxies. It adds up all the brightness from those galaxies in each pixel. That makes it easier to detect the emission in that pixel. There's more emission. And it allows you to map out the large scale structure, like in this plot at the bottom of the slide here, but without having to go through this painstaking and expensive process of looking for individual galaxies. So here's some advantages of doing this with 21 centimeter intensity mapping. So 21 centimeter comes from the fact that we're using neutral hydrogen to do this. It's a very, very common, the most common type of normal matter in the universe, more or less. It just so happens that if you have neutral hydrogen, it has a very well-defined emission line due to a spin flip transition at about a wavelength of 21 centimeters, or that's 1,420 megahertz, if you want to think of it as a frequency. That's well into the radio part of the electromagnetic spectrum. And so if we build a radio telescope, we should be able to pick up the 21 centimeter line from neutral hydrogen. We should be able to do that for many, many, many galaxies all combined together using this intensity mapping technique. And because it's easy to build radio telescopes that give you an output as a function of frequency, that they're spectrometers, we can measure this emission line at many different frequencies. And of course, because of the cosmological expansion, that rest frame frequency of 21 centimeters has been redshifted to lower frequencies. And so when we see this emission line at lower frequencies, we know it's from further away, it's from higher redshift. And so that means we can make 3D maps of the universe. We can do tomography with this type of emission. Now, because it's more efficient than a galaxy survey in this way that I'm talking about, because it just gives you a snapshot of the large scale structure directly, rather than having to count individual galaxies, it's very fast in a way. You can access quite large survey volumes. You can do quite a rapid survey of a very large volume of the universe with a radio telescope. And that's really one of the major advantages. Another major advantage is different galaxies are brighter or fainter at different times in the universe's history. H1, neutral hydrogen, is everywhere. Even though since the epoch of reionization, a large amount of hydrogen has been ionized, there's still plenty of neutral hydrogen kind of hidden away in galaxies, giving off this 21 centimeter emission. And because there's so much of it, because it's everywhere, it gives us what we know as a relatively unbiased tracer. There's wherever you see neutral hydrogen, there's going to be roughly a proportional amount of dark matter there as well. And this is true out to redshift of about 6 or so, when we think the epoch of reionization would have ended. So, the fact that we can use the same tracer of the dark matter from redshift 0 to redshift 6 is excellent. With galaxies or tracers similar to that, you tend to see a lot of evolution in the properties of those galaxies. A galaxy that you see at redshift 0, that's a blue galaxy, is going to look a very different color. You're going to see it at a very different wavelength if you saw it at redshift 6. So you probably need to build a different telescope to see it, and so on and so on. In the radio, with the 21 centimeter emission, that's not true. You can use the same radio telescope, almost, to receive emission from a very wide range of redshifts. And so that's really conducive to doing gigantic surveys, making maps of a very, very large fraction of the universe. So for those of you who haven't come across radio astronomy too much, or you haven't spent much time thinking about this, I just want to give you a very, very, very basic introduction to how a radio telescope works. And you've probably seen these things before, but the general idea is you have a dish, It focuses the radio signal from the sky onto a receiver that's normally positioned above the dish. That dish is also like a kind of lens. It restricts the field of view of the receiver. The receiver can only see kind of directly what's in front of it rather than the whole sky, which is often a good thing. And the receiver itself is almost like a thermometer in some ways. It measures the temperature of the sky, a particular type of temperature that we call the brightness temperature. And as I've already mentioned, radio telescopes are inherently spectrometers. It's very easy to measure the signal at a range of different frequencies with a radio telescope. So by default, or almost for free, you get a spectrum, a frequency spectrum of anything that you look at with a radio telescope. So it's not that simple, of course. So you're doing all this with a gigantic piece of metal. You've got these receivers that, they're very sophisticated these days, but they're still not perfect. So all this electronics adds noise to the signal. But if you observe the sky for longer, the noise averages down. You improve the signal to noise ratio of your measurements. So the longer you stare with a radio telescope, the better the signal to noise, the better you detect the signal you're looking for. You have to calibrate that response. Radio telescopes are quite difficult to calibrate. You need to go and observe something where you know what its frequency spectrum looks like, so you can then use that to calibrate and accurately measure anything else you want to observe. But that's quite difficult. And you also have the problem of radio frequency interference. So things like cell phones, GPS satellites, everything essentially to do with human activity produces radio frequency interference, which kind of puts spikes into your signal and kind of ruins the signal at a particular range of frequencies. So the type of radio telescope I just showed you, that was just a single dish. I'm mostly going to be talking about when we use radio telescopes as a single dish, also known as being in autocorrelation mode. But it's also very common to use radio telescopes together, to connect them together, and to multiply or cross-correlate the signals from them, so they act as an interferometer. And this is something you've seen if you've ever done any interferometry experiments, like a Michelson interferometer. You essentially combine two signals together in such a way that you get constructive and destructive interference, and you can measure the size and brightness of those interference fringes, and they tell you something about whatever you're looking at and the time delay in the light paths between, for example, different arms of an interferometer. With radio telescopes, you're using a very similar effect. You put two radio telescopes down, you point them at the same patch of sky, then you take the signals from them, multiply them together, and because there's a time delay in when the wave front from a radio source reaches one telescope as opposed to another, you'll get an interference pattern, and you can use that to very precisely measure the angular distribution, the distribution of the temperature on the sky. I'm not going to go into tremendous detail about that, but essentially the thing to remember is that the further apart your two receivers are, the longer the baseline. And so the longer the baseline, the more rapidly varying your interference fringes are. And so the finer angular detail you can see. So the resolution of a radio interferometer increases when your dishes are further apart from one another. And you can use this to kind of tune what kind of angular Fourier modes on the sky, essentially, your telescope is sensitive to. You can choose exactly which bit of a Fourier transform of the sky your telescope is sensitive to, just by moving the dishes around. So a big question, especially for 21 centimeter radio cosmology, is what kind of telescope should you use to do this? You tend to find that if people purpose build a telescope in order to detect the 21 centimeter signal, they choose it to be either just a bunch of single dishes or maybe one single dish, this autocorrelation mode with a particular design, or they design it to be an interferometer with many pairs of dishes normally quite closely packed together because most of the angular scales we care about are large scales. So we care about the largest angular scales on the sky, and so interferometers that are closely packed together are most sensitive to those. But as well as that, you also have these general purpose radio telescope arrays, like the Square Kilometre Array. And in fact, you can use those as either a bunch of single dishes or in this interferometer mode where you cross-correlate all the dishes together. And which of those you use will depend on which angular scales you care about, and also the properties of your telescope. So here are just a few very basic hand-wavy expressions to tell you which angular scales each will be sensitive to. If you use your telescope as a single dish, an autocorrelation mode, it will be able to see any angular scales greater than this angle, which is roughly equal to the wavelength you're observing at, lambda, divided by the diameter of the dish. This is an approximate expression, but it's roughly lambda over d. So for something like the SKA, lambda over d is about 1 degree at most of the frequencies, most of the wavelengths you care about. So you really can't see much on small scales. That's all washed out. But on large scales, you can see everything. An interferometer, on the other hand, you're kind of stuck between two limits. You can see angular scales as large as the minimum baseline length permits you. So anything, any angular scale smaller than lambda over d min, and you can see angular scales as small as lambda over d max, the maximum baseline size. So your resolution is limited between these two limits. But in general, by just moving your dishes further apart, you can make d max very large, and so you can get a very, very, very high angular resolution, high enough to do things like what the Event Horizon Telescope did recently, which was to image the accretion disk around a black hole in a nearby galaxy, which requires fantastically high angular resolution. The point is you choose by deciding where to put your dishes. So what does the frequency spectrum look like? Remember I said all these radio telescopes, they're spectrometers. So I just want to show you a little cartoon to tell you, what I really mean by this. So with the 21 centimeter signal, you have an average brightness temperature of all of the 21 centimeter emission at a given frequency. So that's this TB in angle brackets that I'm showing you here, which is a smooth function. And then on top of that, in small pockets, small different regions of the universe, your density of stuff, of dark matter, might be a little bit lower than average. So that would be a negative value of the density contrast delta, or a little bit larger than average, that would be a positive value of delta. And because in regions where you have less stuff, delta is negative, you have less neutral hydrogen, that means you have less 21 centimeter emission, and so you'll see a dip in the spectrum there. And the opposite for if there's more stuff there, if there's more 21 centimeter emission. And so by looking at the frequency spectrum as a function of frequency and seeing these fluctuations going up and down, that's telling you how many overdensities and underdensities you have along the line of sight. And remember, this is a function of frequency, and frequency maps to redshift. So you can measure the distribution of matter as traced by neutral hydrogen along the line of sight as a function of redshift. Now, it would be great if that's all we saw, but it's not. I already mentioned noise. You have noise from your receivers. That's normally quite high, but if you observe for a longer time, your noise averages down. It's just white noise, it averages down. You also have what we call foregrounds, which is the emission from, for example, our own galaxy, the Milky Way, which is very bright, incredibly bright. It's much closer to us than most of this emission. So it completely swamps the 21 centimeter signal. You have to somehow subtract it. And now, fortunately, most of this foreground emission isn't of a similar kind. It's not from a spectral line. It's actually things like synchrotron emission, which has a very smooth frequency spectrum. And so by simply subtracting out the very bright but very smooth contribution as a function of frequency, we should be able to access the 21 centimeter signal again. Of course, it's still not that simple. You also have a bunch of other effects to do with the instrument and how well you've been able to calibrate it, what we would call calibration errors, And there are many, many different types of calibration error here, but that's something that can have more structure than the foregrounds. It can vary with frequency, but it can also have some smoothness to it as well. It really depends on what telescope you're using. So what we need is some way of subtracting out all of this stuff and leaving only the up and down fluctuations due to the 21 centimeter signal. And if we can do that, we can make maps of the large-scale structure of the universe and do cosmology with them. So now I want to talk about, just briefly, a few of the many different experiments that are out there, just to give you a sense of what they look like. And I think there's a kind of rugged beauty to many of these things, because ultimately they're just hunks of metal that have been kind of plonked into the ground in normally a desert somewhere. If you look at these very closely, they're normally made of very low technology materials. In fact, the 4 of the telescopes you can see here, that what they're mostly made of is mesh, what we call chicken wire, which is essentially, you know, the mesh that you would use in agriculture. It's that very flexible metal wire. It's very cheap. It's a radio telescope, so it doesn't have to be a super precisely machined into a shape. You can do quite well, you know, just by having a roughly parabolic shape of your mesh, for example. And so some of these telescopes here, I don't know if you can see the Hera telescope in the middle. That's one of the ones I work on. This is actually in the desert, the Karoo Desert, about 8 hours north of Cape Town in South Africa. And this is a load of chicken wire, a load of mesh, held up on some telegraph poles that have just been hammered into the desert soil and held there with concrete. And then they're all connected together to some very sophisticated electronics in a shipping container. So these things are beautiful. They're really high tech in some ways. The receivers are the most sensitive in the world. The computing power you need to analyze the data is, you know, if you look at the CHIME telescope, for example, some of the computers that analyze the data from that have a higher throughput than, you know, the entire internet in a given day. You know, they're very specialized, but very high performance machines. But then on the other hand, they're also just these lumps of metal that almost look like they're from a scrapyard, and they've just been dumped in the desert. So I think there's a kind of beauty and a kind of symmetry to the fact that these very high tech machines that we're using to look back to the dawn of time are kind of made from the same materials that we would use to keep chickens from escaping from us. So what I'm mostly showing you here, these are all interferometers. These are all telescopes where you have a dish, or many dishes, or many receivers. So you see MWA, it looks like a load of spiders. They're individual receivers without a dish. Or CHIME and Tianlai, you see they have these cylindrical reflectors. They've all been optimized and designed in slightly different ways, but they all do essentially the same thing, which is to have many receivers, and they cross-correlate all the signals together. They multiply them together, and you get these interference fringes, and you can make very sensitive, high-resolution measurements. So I'll show you a few more. Meerkat, the one top left, is another one that I work on. This is a precursor to the square kilometer array. Some of you may also recognize Bingo, or the cliff where at some point Bingo was supposed to be built against, and what's probably now quite an out-of-date mock-up of the receiver and reflector system for Bingo on the right, and then various other telescopes like the Green Bank telescope, GBT, the Parkes telescope in Australia. These are the dishes that have been used in this autocorrelation or single dish mode. Some of them, like Meerkat, you can connect together and use as an interferometer. That's how most people use them, in fact, but we're mostly interested in using them as single dishes, because the resolution that they have, the resolution and the sensitivity that they have is ideal for the kinds of angular scales that we care about. So there's a big divide in the community depending on what type of 21 centimeter emission you're after. So there's the neutral hydrogen that existed before the epoch of reionization and during the epoch of reionization, when the first stars and galaxies switched on and started to ionized neutral stuff like hydrogen. There's one type of telescope that you build for that sort of thing. This is stuff we're seeing between redshift 6 and 20, so quite low frequency. And then you'll build another kind of telescope if you're looking at what we call late time experiments or post epoch of reionization experiments, where mostly what you're seeing is neutral hydrogen inside galaxies that escaped being ionized during the epoch of reionization. So post-EOR experiments are mostly focused on measuring the baryon acoustic oscillations, this preferred distance scale in the clustering of matter that comes from very early times in the universe's history when there was a coupled photon baryon fluid and there were sound waves in it. It's a fantastic way of measuring distances and the expansion rate of the universe, and we're really interested in doing that so we can find things out about dark energy. And for these post-EOR experiments, their design is mostly driven by sensitivity requirements. We want to make them as sensitive as possible to the range of angular scales where the baryon acoustic oscillations are. Just as a reference, that the corresponding co-moving distance scale is about 150 megaparsecs. And we also need to be able to calibrate them very, very accurately because the signal is has such a high dynamic range. Remember, these foregrounds are many thousands of times brighter than the cosmological signal we're interested in. So if you're not able to calibrate it very accurately, instead of seeing the 21 centimeter signal and subtracting the foregrounds, you're going to see a big mash of the two things together, which you don't want. So again, on maybe a slightly more technical point, people also build many element interferometers like Chime and Hyrax that you're seeing here. If you do that for this kind of intensity mapping, you generally want to pack them close together because you care most about large angular scales of a degree or so. But I'm mostly in this talk focusing on the single dish systems that I've already been mentioning. Okay, so on to the next part of the talk. That was all the basics out of the way and some of the experimental landscape. Now I just want to show you a few characteristics of real 21 centimeter data and you know, a way you can think about what these data look like theoretically. So here's a kind of simulation example. The plot you can see here is observed frequency along the x-axis. Remember that can be mapped to redshift for the 21 centimeter emission. And then on a logarithmic y-axis, you've got the brightness temperature. And you can see you've got your foregrounds in red. And then you've got your mean H1, your 21 centimeter signal, and your fluctuations along the line of sight in blue, near the bottom. So you see that there are several orders of magnitude between them. And you can see the structure in the fluctuations of the signal. And that structure is the large scale structure. So the basics of the data are you have this very bright but spectrally smooth foreground emission way above this faint but very rapidly varying 21 centimeter emission. So it's a high dynamic range problem. But we don't see this directly. We see this through a telescope, an instrument that has what we call a highly chromatic, so a highly frequency dependent response. So even very small calibration errors, very small mistakes in how well it's calibrated, can mistakenly give you a quite complicated frequency structure. So that bright, that smooth red line can get turned into something that fluctuates if we don't do a good job of the calibration. And another problem is we have missing Fourier modes. We want to reconstruct the signal using Fourier analysis, but you find that because of the angular resolution of the telescope and the fact that you have to subtract certain modes away in order to, for example, clean out the foregrounds, you lose some Fourier modes of the signal. And so you don't make a true map of the large scale structure. You make a filtered map where you've lost some modes. And that introduces some subtleties in the way you analyze the data. So I'll very briefly just give you a kind of cartoon of how to try and understand this. So let's imagine we're looking at the large scale structure of the universe in a two-dimensional Fourier space. We have a K parallel, which is the radial Fourier mode, the Fourier mode in the line of sight away from us. And we have the K perpendicular, which is the Fourier mode on the sky. So, so the angular Fourier mode. As we've already seen, interferometers and single dishes are only sensitive to certain angular modes. They're only sensitive to a particular range of K perpendicular, which is what you can see with the blue and the red blocks in this diagram here. You can only see certain Fourier modes if you have a single dish or an interferometer experiment. The details don't matter too much here. All these different Ks have labels. Don't worry too much. You just see that interferometers tend to be more sensitive to the higher K perpendicular mode, so higher angular frequency, so smaller angular scales, and single dishes tend to be sensitive to larger angular scales, so smaller values of the K perpendicular wave number. And a ton of other effects mean that you lose other Fourier modes too. Single dishes have poor angular resolution, so I've just explained you lose the high K perpendicular modes. You have filtering for these systematic effects or foreground, so you might lose low K perpendicular and low K parallel modes as those get filtered out, and so on and so forth. So quite a complicated topic, and one I'm not going to do justice here, is this idea of what's called the foreground wedge. So if you're familiar with this field, you've probably come across this before, and it's a bit of a fiddly thing. I'm not going to explain it in detail. If you haven't come across it before, don't worry too much. This is just part of this idea that we're only sensitive to certain Fourier modes. Other Fourier modes have to be filtered out because they're contaminated or we're not sensitive to them. So interferometers in particular have a very strongly chromatic response. They're very frequency dependent. And what this means is, as you measure the Fourier modes on the sky, I've shown you the visibility equation here. The sky we denote by T, the temperature distribution at a particular angle and a particular frequency. You see there's a Fourier kernel there that depends on B. This vector B is your baseline vector. And then there's another thing in there, this A, this is your primary beam function. This is this thing to do with your field of view, the fact that your dish only sees a certain part of the sky. So it's not a full Fourier transform. It's actually a Fourier transform with a kind of window function on it. And the fact that you have that window function, I'm showing you an example of the window function here in this plot. You can see this primary beam shape. That's quite common. It goes up and down. You have nulls and you have higher bits. The fact that that primary beam function has this complicated structure and depends on frequencies means that it modulates your actual sky signal, the temperature T here, when you take this Fourier transform in the way that the equation shows you. And so all this really means is anything, if T was a perfectly smooth function of frequency, this A function, this beam function, which is plotted below, will modulate that smooth function. And so you'll end up getting something that has a much higher frequency or higher frequency structure when you look at it in Fourier space. So again, I won't say too much about this, but what this means is when you look in Fourier space, you end up with this wedge shape. It's called the foreground wedge. So all these bright foregrounds, which are actually spectrally smooth, this kind of beam effect, this modulation of that smooth frequency dependence means that instead of looking like they're just smooth, these foregrounds are just restricted to a particular area of Fourier space where smooth functions should live. They get spread out. They get kind of churned up and chopped up because of this modulation effect. And so that looks like a wedge shape in Fourier space. And so you lose all the modes inside that wedge because they're just outshone by the foregrounds. And here's an example for again, some simulations where you see what this wedge looks like. It depends on what your dish, what your primary beam looks like. And I won't go into the reasons for these different shapes, but you can see all this bright emission here means it's very difficult to see that faint 21 centimeter signal behind it. So some other thoughts on seeing 21 centimeter as a filtered tracer. It complicates cross correlations. If you want to cross correlate your 21 centimeter emission with some other kind of tracer of the large scale structure, you have to be really careful about which Fourier modes you still have in your data and which ones you've lost or had to filter out. You have to keep track of that. It also means that certain Fourier modes are much better measured than others. You have very inhomogeneous noise properties. Some modes are measured very well, some modes are measured very poorly. And if you want to make images from this data, you have a real problem with how to interpret those, because if you take an image, you Fourier transform it, you remove all of the very large scale smooth structure, and then Fourier transform it back, you get something that looks very weird. You've kind of missed all of the large scale properties, but you can still see the fine details. You can do this, for example, with a map of the world. If you Fourier transform it, remove all of the smooth stuff, you can't really see the continents very well anymore, but you can see like individual bits of outlines of the coast of certain countries and stuff. So it tells you something, but it doesn't tell you everything. So you have to be careful with how you interpret these images. For the more experts in the audience, here's an example of where this can cause problems. If you have a 21 centimeter intensity mapping experiment, you will filter out the low k-parallel modes. And the reason for that is those are the modes where most of the foreground contamination lives. You have to remove them, you have to filter them out. But if you then cross-correlate your 21 centimeter signal with a photometric redshift survey, so a survey of galaxies or photometric redshifts, those are galaxies where you don't have very good radial information. You kind of only see Fourier modes at low k-parallel. You've lost the high k-parallel structure because of the redshift uncertainties. And so when you do that cross-correlation, you have to be really careful about how much your filtered 21 centimeter map overlaps with your photo-Z survey and what kind of cosmological information you can get out of it. Another example, we've already talked about the baryon acoustic oscillations, which are really interesting. This is some work done by my student Fraser Kennedy. He's writing a paper on this around about now. And because of the limited angular resolution of your telescope, if you look at the baryon acoustic oscillation feature in the transverse direction, so in the angular direction on the sky, it gets partially smoothed out. You lose some angular information and it broadens the peak. And so depending on whether you're looking at this feature exactly in the radial direction, which is theta equals 0 in this plot, or if you're looking at it exactly in the transverse direction, theta equals 90 in this plot, you may or may not actually see the BAO feature. It might get completely smoothed out and you'll lose a lot of that cosmological information you were hoping to detect. So again, 21 centimeter is a filtered tracer, and the way this filtering is done is really important to understanding exactly how to interpret your data. Again, just some more results from Fraser here. Again, mostly for the experts in the audience, this is now the same correlation function I just plotted for you, but now in two-dimensional redshift space. And we're going from the top left, we have just the pure cosmological correlation function, which is isotropic. We add redshift space distortions in the top right, which is intended to make it anisotropic. And then when you start adding things like a beam effect in the bottom left and then a foreground cut in the bottom right, you see the shape of this thing gets a lot more complicated. And so you need to account for those effects if you're going to interpret this large-scale structure data successfully. So I think I only have about 15 minutes left. I'll give you a brief overview of this Meerkat single dish survey, and then we'll have time to just go through one or two examples of things we should be able to do with intensity mapping in the future that are exciting from a fundamental physics and cosmology perspective. So here's a nice picture of the Meerkat Array, or several dishes in the Karoo Desert. So Meerkat and Hera, two of the experiments I work on, are right next to each other very conveniently. And they're in this beautiful desert about 8 hours north of Cape Town, as I mentioned. Each of these dishes is roughly 13.5 meters across. So they're pretty huge compared to your typical human. And they have two receivers fitted at the moment, an L-band and a UHF band receiver. And they're roughly sensitive to frequencies of between, I think it's about 570 megahertz and about 1700 megahertz. So a wide range of radio frequencies. So there are 64 of these dishes in total. Each dish has, each of these receivers is what we call a single pixel feed. So when you point this at the sky and use it in this single dish mode, whichever direction you're pointing, you get one number from that direction, one number, but as a function of frequency. So you get a spectrum, a kind of one-dimensional spectrum along the line of sight. So if you want to make a map, a two-dimensional map using this, you need to look at many different directions and build up your map pixel by pixel. Again, some technical details for the experts. These are very low noise receivers. They're actually outperforming their kind of their design specifications. They're less than 23 Kelvin noise temperature, these receivers. And the beam, depending on what frequency you're observing at, is between about 50 to 80 arc minutes. So roughly 1 degree beams, which means we can resolve anything above roughly 1 degree if we want to make maps of the large scale structure. So there's a particular survey proposed using Meerkat, which will make use of this intensity mapping technique, as well as doing more conventional radio galaxy surveys. It's proposed to be a 4,000-hour survey, so 4,000 hours is quite a big survey. And it would cover about 4,000 square degrees, again, like a reasonably large chunk of the sky, overlapping with the dark energy survey footprint, dark energy survey being a photometric redshift survey. We're not at the point where we can do the Meerkat survey yet. Meerkat's still a very new telescope. Lots of people want to spend time using it. So we're just doing a Pathfinder survey at the moment. So we recently put out a paper on this, led by Jingying Wang in Cape Town at the University of the Western Cape, but with many others, including some colleagues from Manchester, who I know you will have been in contact with, some of you. And this Pathfinder survey is about 10 hours of total data. So before we remove any nasty stuff, we've got about 10 hours of data on all 64 dishes in the array, used in the single dish mode. And we did this survey over the Wiggles 11-hour field, and that's a roughly 10 degree by 30 degree patch, so roughly 300 square degrees. And we did this as an initial trial of our calibration strategy, which is called a noise diode-based calibration strategy. And I'll just show you a few examples of the data we got from that now. So first of all, what you can see here is the averaged bandpass. So the average signal as a function of frequency along the x-axis, and the pale, the white areas are the ones we've kept, and the gray bands are the ones we've thrown away because you see all these spikes. These spikes are radio frequency interference, and it's quite bad. And you know, a lot of this is due to terrestrial television or GPS satellites. Not too much we can do about it. Maybe we can improve the size of those white bands a little bit, but it's still quite a challenging RFI environment. And of course, that limits which redshift ranges you're ultimately sensitive to. Now, the way we use these 64 dishes is we scan them back and forth. Remember, each dish just gives you one number as a function of frequency in each direction. So we don't just look at one direction, look at the next direction, you know, do stop and stare. We actually scan back and forth. This is very much like a cosmic microwave background experiment. And then we use something called a map maker, which combines all of those scans together into a map. And the way we do the scans is by scanning the telescopes back and forth at a constant elevation. And as time goes by, the sky rotates. I mean, the Earth rotates, but the sky appears to rotate. And so we make a map of a larger region. Now, the way we calibrate this data is by injecting a noise diode signal. A noise diode is just a small piece of the instrument internal to the receivers that just inject a very reliable and dependable amount of extra temperature for a very brief period. And because we know it's reliable and dependable, we can measure it once, and then as time goes by, we can see how the size of these little jumps varies, and those little jumps, that allows us to calibrate the instrument in a relative way. It doesn't tell us what the absolute temperature of the sky is, but it allows us to smooth out any variations in the calibration. And so we turn the noise diode on for roughly 2 seconds every 20 seconds. And this is a strategy that hasn't really been tried on the Meerkat telescope before, and it works. So we're all very happy about that. And then here are just some results. Here's a map at a particular frequency. Remember, we can measure similar maps to this at many, many different frequencies. This is just a particular frequency at about 1,023 megahertz, showing the data we get, and you can kind of see the pattern, this scan pattern, where we're missing some pixels because we didn't scan over them enough times. And at the top, you see the galactic model, these galactic foregrounds taken from an external source, the PISN model in this case. In the middle, you see our calibrated data. And at the bottom, you see the residual, the difference between those two. And anything you see in the residual, if we've done a very good job of calibrating it, that should just be purely noise. Any point sources, any other particular points of emission that weren't part of the galactic model, and any 21 centimeter emission. We haven't observed for long enough to make the noise level low enough to see the 21 centimeter emission yet. That will require more survey time. But hopefully from the residual, you can see that it's actually done a pretty good job of seeing these individual magenta points here, which are known radio sources. And if you look at the middle panel and compare with the top panel, you can hopefully see that we do a good job of reproducing a lot of the large scale structure as well. It's not perfect, but this is not a bad calibration at all for an initial attempt. We need to improve it, but this is good progress, I think. So in the last few minutes, I just want to talk about a few different scientific examples of how we can use 21 centimeter emission for future applications in cosmology. So as I mentioned, most of these current batch of experiments, including the way we use Meerkat, things like CHIME, things like Bingo, they're mostly optimized to detect the baryon acoustic oscillation feature. And that's a really important thing to go after. But there's a lot of other stuff you can do as well. So if we look at the unique capabilities of intensity mapping compared to things like a galaxy survey, I've already mentioned you have these high survey speeds. You can very rapidly survey a massive, just a gigantic 3-dimensional volume of the universe out to quite high redshift with spectroscopic redshift information. These things also integrate all of the emission from a given spatial volume. If you do a galaxy survey, you just see where individual galaxies are. If you do intensity mapping, you get all of the emission. So it's an integral probe of your luminosity function. If there are very faint objects mixed in there as well, they'll be in your data somewhere. And then, as I've already mentioned previously, H1, neutral hydrogen, is a relatively unbiased tracer. And there are certain applications where that's quite useful as well, which I won't go into too much. Why might you be interested in looking at high redshifts? I mentioned that this type of survey can go out to higher redshifts than your typical galaxy survey. Doesn't it seem like most of the interesting stuff is going on at lower redshifts, redshift 2 or less, where cosmic acceleration or dark energy is happening, or higher redshifts where you're looking at the epoch of reionization? So isn't this range of redshifts that we would call high redshifts in the post-DOR time period, isn't that a bit boring? Is there any point looking at it? And I just want to make an argument for that being an interesting period of cosmic history. The dark energy we see today may behave a lot like a cosmological constant, but at this exact redshift range, at these higher redshifts, there are good reasons why in some dark energy models, and in fact many dark energy models, you'd expect to see a behavior that deviates from a cosmological constant. I call this a tracking or attractor behavior. But the point is, it wouldn't just look like a cosmological constant, and so we would catch dark energy in the act of not being a cosmological constant. So already that's interesting. This is also a good redshift range to do things like make more precise measurements of the spatial curvature of the universe, which can tell us about different models of inflation. It's a good place to look for primordial non-Gaussianity on very large scales. it's a good place to look at an independent way of measuring the total sum of the masses of all the neutrinos, and also just purely because we know the universe was simpler in some ways at these higher redshifts. Instead of being a lambda CDM universe with dark energy or a cosmological constant, it behaved much closer to what we call an Einstein de Sitter universe, where only matter is the dominant form of energy content. And so it's a useful reference point as well. So again, I'm not going to spend too much time on this. I just want to show you some of the possibilities. So this is the point I was making about different theories of dark energy predicting a deviation from a cosmological constant at these higher redshifts. What we did here in these papers led by Marco Roveri, and I followed it up recently this year, is we did a Monte Carlo exploration of the entire class of a very broad type of dark energy models called Horndeski models. And we just looked at what the typical equation of state of dark energy of those models was as a function of redshift. And you can see that here in this plot. You see at low redshift, they mostly look like a cosmological constant. But if you can go to redshift 2, 3, 4, and above, it's harder to see the dark energy there. It's not as big a fraction of the cosmological energy density at those times, but it has a different behavior. It has a different equation of state. And so if we were able to measure or catch dark energy in the act of its equation of state changing, that will tell us a lot about the physics of dark energy. I also mentioned spatial curvature as well. I won't go into the argument too much here, but there are various big subclasses of inflationary model where if you did detect even a small amount of spatial curvature in the universe, it would falsify those entire classes of inflation model. Most of them predict curvature to be very, very small. So we've measured the curvature to be small, but not necessarily zero. We've put upper limits on it. If you're able to go and measure it at the level of something like 10 to the minus 3 or 10 to the minus 4, that would rule out a lot of these models. I mentioned massive neutrinos. I don't want to spend too much time on that, but you would be able to improve your neutrino mass measurements. And also I want to mention ultra large scales. The fact that these intensity mapping experiments can survey very large volumes of the universe means that we can actually see Fourier modes. We can see the large scale structure on the scale of the cosmic horizon, really the largest possible Fourier modes in the observable universe. And there are lots of interesting inflationary and general relativistic effects that these ultra large scales are sensitive to. And it's very hard to access those using any experiment. Perhaps intensity mapping is the best way of doing a very efficient, rapid survey of these very large scales, and we can learn something about fundamental physics from those. And again, I'll skip past this, but there's a way of doing that in concert with other types of survey as well to help reduce some of the noise, what we call a cosmic variance calculation, cancellation on these observations. So to finish off and to summarize, intensity mapping is a young method. It has lots of problems. We're really getting to grips with them at the moment. They're tough problems. We think we can solve them, but it's a lot of work. But I think it'll be worth it because these things can improve on more traditional galaxy surveys in several different interesting ways. I've mentioned what we can do at high redshift and why there are compelling reasons to look at higher redshifts than a typical galaxy survey can detect. And also why it might be interesting to look at ultra large scales, which are difficult no matter what method you use. Maybe an intensity mapping survey is the best way of accessing those. So there's still lots of work to do. I hope at least those of you who are interested or involved in bingo are having lots of fun with the data as well. And even though radio telescopes are complicated, there's lots of cool stuff we can do with them. So we should keep pushing them harder and trying to figure out some of these mysteries of the universe as best we can. Okay, so I'll finish there. Thank you very much for your attention. And yeah, thanks for inviting me.
Thanks a lot, Phil. It's nice, very nice talk. I think it was very motivating. And let's open up for questions. Questions, people? You can make You can make your question in Portuguese if you want, and then I try to translate to Phil. Or you can also write in the Q&A.
You should also feel welcome to email me if you have any questions as well. I'm always happy to talk about this stuff. If you prefer to.
Okay. Then actually, I would like to just while people are figure out some questions, let me just if you can make some comment on this diode calibration. How, I mean, this is where you put this diode, where you exactly put it, because it also seems to require some engineering to do it, right?
Yeah, absolutely. So with Meerkat, it was I don't think it was always intended to be there in the design, but enough people. I think we took the engineers out for enough beers that they agreed to build it into the design eventually. And so generally it comes after the first bits of the receiver and the first I guess set of amplifiers. Let me make sure. Yes, so it's normally quite close to the start of the receiver, but a little way back. I'm not an engineer, so I can't really.
No, that's okay. That's
explain
okay.
in
But
much more detail. But yeah, you want the noise diode to go through as much of the rest of the instrument as you possibly can, so it gets affected by the same effects as the signal. You wouldn't just have a noise diode that you shine into the dish. That would cause lots of problems, I think. But quite soon after you've initially brought the signal into your electronics, I think is where you normally want your noise diode to be. And so because these noise diodes can be manufactured in a very precise way, I think they're supposed to be stable to certainly better than 1%, maybe significantly better than that. Again, I'd have to ask the engineers, but because they're very stable, even as your signal and your calibration varies, you can rely on this signal as a kind of, you always know that it should be the same, and so you can do a relative calibration and use it as a fixed reference point as a function of time. And this is something we intend to use for SKA as well. It's something that the Green Bank telescope used as well. I'm not sure if the plan is to do this with Bingo, because I know you have a different kind of receiver. I think you have a pseudo correlation receiver that doesn't need calibrating as regularly.
Yeah, but we still need some calibration strategy to different complications actually.
Yeah.
So any question now? We can on physics, instrumentation, anything?
Yeah, Milka.
Yes.
Yes.
Marcelo, go on.
Yeah. Hi, Phil. Marcelo here.
Hey, how are you doing?
Hi, Neil.
Yeah, good.
I have a question. It's more kind of. It's not exactly a question, just to ask some about some comments on the technology used in Bingo. It's very different than when you use a single dish or many dishes. Bingo is only one dish with many detectors. So it's the same as used in parks or in China, right? So do you think that this configuration may give some special feature good for cosmology or something else?
Yeah, absolutely. I mean, it means so instead of seeing one pixel at a time like Meerkat does, it means you see many pixels at a time. It's a multi-pixel feed.
Pixel with one dish. Yeah.
And you have one very big reflector, but you can tune that and tune the focal length so that you have a really big field of view. So there are definitely some advantages to doing that. You can kind of survey many pixels at the same time. But I think there'll also be some complications as well. So for example, because you have all of your pixels, all of your detectors, let's call them, very close together, you'll probably have some amount of crosstalk between them. So these radio telescopes, they're really very, very sensitive electromagnetic objects. And so even in Hera, we see these dishes in Hera, which are something like 14 or 15 meters apart from one another. Neighboring receivers kind of detect when another receiver is detecting something. They kind of talk to each other in a way that we don't want them to. They're not isolated from one another. And so you end up seeing these common signals that the receivers see the same thing at the same time, which isn't what you want from an interferometer. And it gets put into your signal. It's a bit different for bingo because you have a single dish, you're trying to do autocorrelation, but you'll find that you might get things like noise correlations between receivers or stuff like that. So it will be super interesting to see what noise properties the receivers end up with eventually, because I bet they won't just be simple, straightforward white noise. I bet there'll be lots of more interesting stuff going on.
Okay. Okay. Thanks a lot, Phil. So it was great. Now I think we should close because there is still another talk and we are running out of time. It was great to listen to you. Great talk. Thanks a lot.
No, thank you so much for having me. I'll stop sharing now, and yeah, all the best to all of you, and we have a happy Christmas and holiday season.
Same to you. And take care.
Thanks, folks. See ya.
So, here is Richard Battye around. So I'll, okay, it's already in the screen. So let me introduce Professor Richard Battye. He's a professor at the University of Manchester. He got his PhD in Cambridge University and did some postdoc at Trinity College and at Imperial College and also at Cambridge University. He is one of the members of the Bingo collaboration. So nice to have you here. Richard, you can start anytime you want.
Okay, can you hear me?
Yes, very good.
Good. I can't see you. I can only see my talk. Okay.
Yeah. But we are listening to you very, very clearly. Don't worry.
Okay, good. Okay, well, thank you very much for asking me to give this talk. And I can remember coming to Campina Grande about 1.5 years ago, associated with the Bingo telescope, and I think I met some of you then. It's nice to give this talk online, and I'm going to talk about something. It's not totally unrelated to what Phil was just talking about, but slightly different. And so we know that the universe is full of dark matter. Well, we have very, very strong evidence that it is full of dark matter. But we don't know what it is. We don't know what the particle is that's causing this. And there are very, very many ideas around, but one of the strongest ideas over a long period of time has been the idea that it's what's called an axion, or a dark matter axion. And what I'm going to talk about is the possible detection of such a particle, a spectral line from such a particle in the radio millimeter wave band. And this is based on a paper that was on the archive about 1 year ago, and published in Physrd with collaborators below, and particularly I've underlined Jamie MacDonald and Shankar Srinivasan, who are the two junior members of the collaboration and the two who, of course, did most of the work there. So I'm going to do an introduction to axions, and then I'm going to talk about spontaneous emission from dark matter halos, and potential for stimulated emission from dark matter halos, and conclude, I think, that it will be very difficult to detect this Axion signal from those processes in large-scale structure. But then I'm going to go on and talk about the decay of axions in a magnetic field, and in particular, resonant decay of these axions induced by the plasma, the decay of the axions in a plasma where the mass of the axion is equal to the plasma mass. And this can lead to quite a strong signal, potentially in the vicinity of a neutron star, which has a very large magnetic field. I'll talk about the width of this spectral line and the concept of Doppler broadening, which is really important for estimating this. And then ultimately, I will talk about some limits that people have used, some people have published based on this idea that in the literature using recent observations, which are competitive with the very best other ways of trying to constrain axions. So the origin of the axion is what's known as the strong CP problem. And the strong CP problem is that there are no CP violating strong interactions that have ever been discovered. And there is a constraint on that from the neutron-electron dipole moment measurements, which constrain these CP violating strong interactions, not weak. So there are CP violating weak interactions, but not CP violating strong interactions to be 1 part in 10 to the 10. However, QCD predicts that there are, and they are non-perturbative effects with this associated with a term F dual F in the Lagrangian, and this angle theta that's in the first equation up there. So the electron dipole moment measurements constrain this number to be less than 10 to the minus 10. So it's a dimensionless number in a Lagrangian, and having those numbers very, very small is deemed to be bad on theoretical grounds, and that is what's known as the strong CP problem. Now, there is a solution to this, which is known as Peccei-Quinn symmetry, and that is to make the angle theta a dynamical variable. And associated with that dynamical variable is the possibility of a pseudo Nambu-Goldstone boson predicted by Weinberg and Wilczek in 1978, which is the Goldstone mode associated with the breaking of this symmetry. And the particle will be expected to become massive at the QCD phase transition due to instanton effects. And if it becomes massive, then it can become a dark matter candidate. And because it is, because of the way that it's created, it can be a cold dark matter candidate, and that is what we are looking for. So the axion is a term that's used rather ubiquitously in theoretical physics to describe any kind of U1 symmetry. But I'm talking specifically about the axions as a dark matter candidate. And what we have to do is create a particle. What you need is a particle that has a density omega axion h squared equal to 0.12, which is the measured Planck cold dark matter density. And there are 3 possible ways of creating this. One is a thermal production, which leads to EV scale axions, which would be detected in the optical near infrared. There's so-called misalignment production, which predicts axions around 20 micro EV, which is the radio wavelength, which I'll talk about in a second. And there's possibility of creating them in the axion due to the decay of axion strings around 100 to 400 micro EV, which is a radio millimeter waveband. So here's a summary of what we're looking for. So there will be two parameters in the model. One is the mass, Okay, and this pink colored line here is the misalignment production. The blue is the region where you would get them from string decays. There are already some experiments, ADMX and Haystack, which are terrestrial haloscopes, which have ruled out various regions of this space. And the other dimension is GA gamma gamma, which is the axion to photon coupling. And that is one of the things that we're interested in. So note that there is an upper limit on GA gamma gamma around 10 to the minus 10 from the CAST solar haloscope, solar helioscope, which is based in CERN. So as I said, the interactions of axions with photons are quantified by two parameters, the mass and the photon coupling, and specific models that you might come across. So there are a couple that are very common called DFSZ and KSVZ. These make a connection between those two parameters. And if you look back to my slide here, the orange dashed dot line and the blue dashed line are these two. One of them is DFSZ and the other one is KSVZ. So the axion will spontaneously decay into two photons and create a photon which is whose frequency is half the rest mass of the rest mass energy of the photon divided by the Planck constant. And the decay timescale for that is about, if I use 10 to the minus 10, which is the sort of present CAS limit, and an axion mass in the middle of the string-based range, it's about 250 micro AV. Then it's something like 10 to the 36 seconds is the decay time. But this is very similar to the neutral hydrogen that we were just talking about, apart from the fact that the decay lifetime is about 10 to the 20 times longer. But it is actually emitted not from the neutral hydrogen, but from the dark matter itself, if the dark matter is made from axions. So what we can do is, by almost adapting the calculations that we used for 21 centimeter intensity mapping, we can work out for a dark matter halo, whose amplitude is parameterized by the surface mass density, sigma, that we can work out what the brightness temperature we'd expect to detect would be. And it's about 100 picokelvin. So pico is 10 to the minus 12 for those who aren't familiar with that unit. So it's a very, very small number. One can have stimulated decay of the axions. So one of the the axions will be interacting with the cosmic microwave background, for example, or any other photons that are emitted. And you can add additional terms to the Boltzmann equation, and this leads to a modified decay rate, which will have a tendency to shorten the decay rate. And for example, for the CMB, this factor F effective becomes FCMB, and which is given by the Planck density function with an energy given by the rest mass energy of the axion. And well, if for small masses less than 470 micro AV, you get this enhancement of the signal. So here are some estimates of potential detectability of this signal. So dependent on what this surface mass density is. So that for a typical average galaxy, the surface mass density averaged over a galaxy is about 0.07 of a kilogram per meter squared. So that's over a whole galaxy. Right in the center, you might expect it to go up to maybe be 100 times as big as that in the center. So it could be as high as 7. And that's what these solid lines are. The dashed lines are detector noise levels. So for a single pixel receiver, it could be about 10 millikelvin per second noise level. And in 1 year of integration, you might be able to get down to this line here. And if you had 100 such receivers, you might get down to this level here. So potentially something like 7 kilograms per meter squared is detectable in a year with a system that could have a sufficient resolution to find a region which had 7 kilograms per meter squared, which would have to be the center of a galaxy, or and you would require probably about 100 pixels. So that is quite difficult to achieve, but not totally and utterly impossible. I'm definitely thinking about designs for such a thing. But there's something that can enhance this decay, and that is in the presence of a magnetic field, a very large magnetic field. So this is a slightly change of tact here. So we can look at Axion electrodynamics is a modification to Maxwell's laws with the addition of terms which involve the interaction Ga gamma gamma with the magnetic field, particularly in the electric field of electromagnetism, via these terms here. If we expand around a magnetic field dominated background, so 0 electric field and a B0, 0 rho, and a background which has a conductivity given by sigma, then these equations can be written like this. So you get an equation for the axion. It's a D'Alembert with a mass, Klein-Gordon type equation, interacting with the electric field and B0, and then the electric field has it's what you would get for example in a metal. The left hand side is what you would have in a metal with a conductivity sigma, which leads to the skin depth calculation at the undergraduate level, and then you get this extra term which is the axion. Interacting with the magnetic field. So what we're trying to think about here is an axion wave coming in from plus infinity. So these boundary conditions here, I've got an axion wave coming in from plus infinity, and I'm going to turn this problem into it essentially becomes like the Schrödinger equation, the barrier penetration problem in Schrödinger's equation, but with two fields. One is the axion, and the other one is the longitudinal component of the electric field. So we're talking about an axion coming in from the left as you look at it, and there's some region where the magnetic field is goes up to some value B0 and go back down, and the axion comes in, and during that time it can basically turn into a photon. It can turn back from the photon into an axion and vice versa, and just keep doing that. Under certain circumstances, there is a resonant effect, and that resonance happens. So you can basically turn that equation into a first order equation, and it happens when the axion wave and the photon wave actually have the same mass. And so you may not be used to the idea of a photon having a mass, but in a plasma it will have a mass due to the interactions with the plasma. And at the point where the plasma density is such that the axion mass and the plasma mass, or the plasma frequency, there should be a squared there on that equation, are the same, then you get this resonant enhancement, and you can work out the probability of an axion turning into a photon as it goes through this region here. Okay, so it comes in from the left, there's some probability of transmission. And this calculation is, as I say, very, very similar to the calculation of the barrier penetration problem in quantum mechanics, but there are two components. So it's actually very similar to what's called the Landau-Zener problem in quantum mechanics, because there are two components rather than one. So this can be of interest in the context of a neutron star. So a neutron star is a sort of order of a solar mass blob of neutrons, which has a radius of about 10 kilometers. They tend to spin and have a magnetic axis, and the magnetic fields, as measured from pulsar observations, so this magnetic axis is often associated with regular pulsing of regular pulsing of radio emission. One can actually model and measure the magnetic fields, and people come up with numbers of order 10 to the 14 to the 10 to the 15 Gauss. And in such large magnetic fields, you can potentially have a sufficient sufficient transforming of axions into electrons that we can potentially detect it. So the picture is that here's the neutron star in the middle, and there is some critical radius around it in the magnetosphere of the neutron star, where the axion, where the plasma frequency is equal to the mass. And in that region, and it has a sort of, it's relatively narrow, but it's not a zero width. You can, and it's about 200 kilometers out for typical masses from the neutron star. You can get a resonant enhancement in that region, which is sufficiently large for us to detect remarkably. So the way that we model this is we model the electron density using what's something called the Goldrich-Julian model, which gives us the number density of electrons in terms of the spin frequency of the neutron star and the magnetic field. And there's a whole series of authors who've studied this problem with varying degrees of improvements over time. So we can calculate the luminosity that we would expect for such a thing, and it's basically just the rest mass energy of the axions in that volume of that spherical shell around the neutron star at a radius of about 100 kilometers with a width of maybe 20 kilometers. And the amount of energy in that area divided by some effective lifetime. So the effective lifetime in such large magnetic fields now becomes typically seconds rather than 10 to the 35 seconds. And although it's a very small region of the universe, you can get sufficient transformation of photons into axions. So we estimate this by the volume of the resonant region, the density of axions there, and the transition probability that's calculated from the Axion electron dynamics, and the crossing time, and the speed with which the axions are moving there. The axions are sort of presumed to have fallen in to the potential well of the neutron star and gained a velocity which is related to the mass of the neutron star. So the luminosity is not what you detect. You detect what's called the flux density, which is the luminosity divided by 4 pi d squared. That's the Euclidean formula for flux. And then you have to essentially divide by the bandwidth to get the flux density. So there's a certain amount of power goes into a region of frequency space, which is a particular amplitude. So the question is, what is this what is this? What is the width of this spectral line? This is where there's some slight differences in people's calculations. So one option is that the width of the spectral line is essentially set by the velocity dispersion of the dark matter halo, delta V, which is of order a few hundred kilometers a second. So if, let's say, it was 300 kilometers a second, then we'd get a delta F over F, which is delta V over C squared, the model that these guys, Hook et al. Came up with, and it's about 10 to the minus 6. And if you then put that into the formula from the earlier calculation, it's about 100 microjanskis. So definitely detectable. If you we've made a suggestion that it's a little bit more complicated than that. That the surface, the critical surface, assuming that the pulsar is or neutron star is an oblique rotator, the intersection of the plane perpendicular to the rotation axis with the critical surface takes the form of an ellipse, as I've drawn here, with some ellipticity epsilon. And when the axion comes in, it interacts with the critical surface and transfers momentum to the magnetosphere. And this corresponds to the Doppler effect from a reflection from a moving mirror. And we've made then some estimate of delta F over F. And we get, so there's a detailed calculation in our paper, but it's omega times the radius squared of the critical surface times by some geometrical factor, which is, in this case, if it is exactly an ellipse, then it's epsilon squared divided by C. And if you work out what that is, it's 10 to the minus 4. So it's a much larger bandwidth. Okay, so if you remember, this number is fixed by this calculation here, L over 4 pi d squared, okay, for a given pulsar. Then you're dividing by a bigger number, and therefore you get a smaller flux density of the order 1 microjansky. So perhaps, we made an estimate of this, and we are now doing more detailed calculations. Typically, current thinking is it's perhaps somewhere between these two estimates of about 10 to the minus 6 and 10 to the minus 4 by doing some more detailed modeling and actually trying to I mean, this is a very simplistic model of the pulsar magnetosphere, and we're doing a bit more complicated modeling, and we will hopefully come up with a number quite soon. Based on our estimates, we believe that limits on, so this is the plot that I had before, right at the beginning, of GA gamma gamma against MAC squared for these are the Axion models, and these guys up here are the red and the green curves here are potential limits that you might be able to get with a 300-meter telescope between 300 megahertz and 10 gigahertz. So in one case, it's if epsilon squared is 1, or if epsilon squared is 0.1, that will change the size of this is the geometric factor, depending on how circular the ellipse is. It changes the amplitude. And this is for an SKA band 5 receiver, which probes a different mass range due to being a different frequency range. So, in fact, people have actually tried to do this with some recent observations. So Foster et al. Have published a paper in PRL in 2020 using the GBT and Effelsberg for an isolator pulsar. They use the simple model for the estimate of the bandwidth. So they ignore this effect of Doppler broadening, which would change their limits by up to a factor of 100. But nonetheless, these are the observations that they have here. So these are their exclusion limits dependent on various parameters of their observations, and they're in the region of 10 to the minus 11, 10 to the minus 12. So this line here at 10 to the minus 10, this is the CAST limit. This is the best limit from these helioscopes. So in principle, these measurements can potentially improve quite substantially upon that CAS limit, but they do depend on the detailed modeling of this pulsar magnetosphere, which, much as I believe our calculations give the right order of magnitude, I'm not totally convinced at the moment that they are sufficiently accurate to start ruling things out. This is another observation by Darling et al., published in APJ Letters very, very recently, using the JVLA. So this is over a very wide range of frequencies. So this is 1.2 to 1.6 gigahertz, 2.4 to 2.7 gigahertz, and a very small range of masses. But this one's actually goes all the way from right down here, which is about 5 gigahertz, all the way up to 30 gigahertz in all the atmospheric bands. And this calculation depends on the local density of axions, which is unknown in the center of the galaxy. So if you believe that the galaxy has an NFW profile in the middle, then you get these purple lines. And if you believe it has what's called some spike model, that a much more sharp spike in the middle of dark matter, then you get this number. Anyway, those things there are the current state of the art. So we're working on these theoretical calculations to try and improve them. I'll conclude now. Detection from halos will be difficult directly from the dark matter themselves, spontaneous decay, but this resonant decay from neutron stars is a much stronger signal. However, there are some uncertainties that need to be understood, I think, before you can start really taking those limits at absolute face value. And that is what we're working on at the moment, understanding the nature of the pulsar magnetosphere and this line width calculation. So what we're actually trying to do is doing ray tracing of and solving Hamilton's equations for the evolution of photons through a plasma in the magnetosphere, and trying to measure these things more accurately. Bespoke observations have already been done to do this, and in fact, at Jogger Bank, we have 12 years of pulsar observations that have been done with our own telescope to try and. So what we're going to try and do is use those observations to reprocess them to look for this effect. Okay,
Okay, Richard, thanks a lot for the nice talk. Let us hear from the audience some questions. Any question, people? Hello, any question? Perguntas? You can ask in Portuguese questions. So while people are pondering about the questions, let me ask my question, if I'm allowed. When you're looking at the signal for this pulsar observations, you are comparing the profile of the pulsars, or is something else?
Sorry, you mean the?
Yeah, in this pulsars that you are looking for, these axions, what kind of observable in the pulsar you are looking for? I mean,
okay, so well, it's
profile or what?
It's just a spectral line in the in the direction of the pulsar.
But
basically,
then
it's static. It's a static spectral line.
I see. I see.
That's what people have done. Now, it's possible that there is a time-dependent signal as well. And that's one of the, I haven't mentioned that, but there is a possibility that there's a time-dependent signal that will so there's there's the electromagnetic pulse associated with the magnetic axis spinning, and people detect that, and that's actually much easier to measure than any the spectral line in the direction of the pulsar. So if it has a time-dependent signal, it could be quite interesting, but we haven't actually, well, we think there probably is, but we're still calculating it. But these measurements here are basically just point the telescope at the pulsar, and then they look for us, they look for the detection of a spectral line of a given width in the direction of that pulsar. And well, they didn't find one, so they then set an upper limit on the flux density of that pulse, which definitely, I believe, then they can transfer that using these kind of formulae up here, which I've sort of sketched about, this one about the calculating the luminosity and the flux density to essentially, and the magnetic field of the pulsar, for example, and you can essentially come up with a limit. That's basically how they work.
Okay. And how do you choose the pulsars to observe? There is some particular type of
yes, ideally there would be a pulsar that was very close, that had a very large magnetic field. That would be but that's typically, they are in the center of the galaxy, or near the center of the galaxy anyway. So it's a sort of trade-off between distance, which you often know where these things are, and the magnetic fields that they measure from the pulsars and things like that. They can actually establish an estimate for the magnetic fields. But the other thing that goes into it is the local dark matter density. So we know what the local dark matter density is around us, or we think we do anyway, if it's a smooth halo. 0.445 GeV per c squared, cc, but in the center of the galaxy we don't actually know exactly what it is, and that was when I was referring here to the NFW and the spike. I mean, these limits here also depend, from Darling et al., depend on what the center of the galaxy looks like in terms of its dark matter profile.
Oh, I see. Okay, thanks. Any other question? So I'd like to thanks Richard for the nice talk and answering me. And so it's nice to have you here, and hope you come again to Campina Grande.
Thank you.
Okay. Bye-bye.
Okay. Okay, thank you again, Richard. It is really a pleasure to have you here among us again. And thank you for the nice talk. And also, I'd like to inform all the participants and the lecturers that we're going to have a break now for lunch. So we go back at 2 p.m. here in Brazil. And I hope to see you guys soon. And then we are going to have our section for the afternoon, which is going to start at 2 and it's going to finish at 6 p.m. So thank you so much again, and see you there soon.
Bye-bye from my side.